Hello and welcome to this recorded learning on embedded system design with the PowerPC 440 processor core. My name is Frank Nelson. I'm a Xilinx technical trainer and course developer. I'll be your instructor for this module. In this module, we will learn about the PowerPC 440's feature set. This module introduces you to the processor architecture and explains its benefits. We're also going to show you how to optimize some of the features of your embedded system with the base system builder. After listening to this recording, you should listen to the other RELs on embedded design. These include the embedded design with the Embedded Developers Kit, that is Xilinx's software package for embedded design, and embedded design with the MicroBlaze soft processor core. These remaining modules complete the course offering. The information in these recorded learnings is essential to the success of our customers as they build their embedded design. However, due to our own time limitations, we cannot teach you everything you need to know about EDK or embedded design, so we encourage you to attend one of our embedded design courses. We'll discuss their content a little bit at the end. So again, welcome to this recorded learning about the PowerPC and embedded design. If you're new to embedded design with one of Xilinx's FPGAs, this module will explain why you may want to use the PowerPC 440 processor that's available to you in the Virtex 5 FX FPGA family. You should also be able to understand the basics of the PowerPC 440 processor after completing this REL. That information is essential if you're going to select an appropriate FPGA device family, or more importantly, build a successful embedded design. The Embedded Developers Kit software, called EDK, is designed to make building a fast, embedded design easy, so we'll cover a little bit of its functionality from the base system builder. But again, to get more information about that, check out that REL I mentioned. After completing this module, you should be able to explain some of the benefits of the PowerPC 440 processor, explain how the utilities included within the Embedded Developers Kit are optimized for the PowerPC 440, specifically in this case as the base system builder, and be able to basically build a system with the base system builder in less than 30 minutes or so. And this will make it easy for you to build your embedded system, so I can't encourage you enough to check out that utility. And we'll have a chance to talk a bit more about that later on. So our first topic will be to introduce you to the PowerPC 440 processor and discuss typical embedded hardware. The PowerPC 440 is available from the Xilinx Virtex 5 FX family and is dedicated in the silicon. This means that it can obtain higher performance and have a top speed of over 450 MHz. Now, don't forget that the PowerPC 440 we use is the same as the off-the-shelf version. There has been no optimizing or simplifying of its architecture. It is literally the same ASIC, just fused to the FPGA's interconnect. Xilinx's embedded processor solutions include the MicroBlaze soft processor core as well as the PowerPC 440 hard processor core. Now, MicroBlaze is a soft processor core, which means that it is built with standard FPGA logic resources, including LUTs and registers, and it can target any of Xilinx's FPGAs. Now, MicroBlaze is a 32-bit RISC processor that can obtain performance over 300 MHz, but this again will depend on the device family and speed grade as well as the embedded system that you choose to build. Both of these processors use the PLB v46 bus standard, and EDK includes IP that is optimized for this bus standard. This means that any IP that is optimized for the PowerPC 440 can be used on a MicroBlaze system and vice versa. Xilinx also provides a PowerPC 405 processor core in the Virtex 4 FX product family. This processor uses a different bus standard than the MicroBlaze or the PowerPC 440 cores. There are several embedded development kits available from a few different manufacturers. Each has its own unique components added to make prototyping fast and easy, and there are a number of different FPGAs to choose from. There are also some that are very inexpensive. To learn more about those available demo kits, go to Xilinx's website at www.support.xilinx.com. Now, as I mentioned, the PowerPC 440 is only included in the Virtex 5 FXT device family. MicroBlaze allows designers to target all of our FPGAs, and these include the low-cost Spartan device families as well as the high-speed Virtex families. So the user, when they're targeting MicroBlaze, is left with a great deal of flexibility to choose a device that meets their cost and performance needs. All of these processor solutions are supported with EDK and include optimized peripherals that save customers from having to build the same IP over and over and build it from scratch for that matter. Note that Xilinx's newest family members, the Spartan 6 and the Vertex 6 device families, already support microblaze and do not have a dedicated PowerPC processor core. A Xilinx embedded system can be nearly any computing system. It is typically single-functioned so that it is small and efficient. This is beneficial to FPGA customers because they don't have to purchase an expensive off-the-shelf component that may already have a large number of peripherals already added. The FPGA solution allows customers to add only the peripherals they need and build any custom peripherals they can't get from an off-the-shelf component. To help with design construction, Xilinx provides a library of verified peripherals that you can add to your system at no extra cost. Typical embedded systems are tuned for low cost, minimal power consumption, relative speed, and minimal FPGA resource utilization. As you may know, many customers like to store their software code inside of the FPGA block RAM. The caveat to this, however, is that there is a limited number of block RAMs inside of the FPGA. But this will depend on the device family and, of course, the density of FPGA you decide to purchase. Typically, most customers choose to use an off-chip memory for their application if they need a large amount of software, such is the case if they need an embedded RTOS. To aid this, EDK includes a number of optimized off-chip memory controllers that support a variety of types of memory components. Spartan 6 even includes a dedicated programmable memory controller that allows you to target most popular memory components in the industry. This is a typical embedded system targeting the PowerPC 440. The PowerPC supports one bus standard, that is the PLB V46. The PLB is designed for 128-bit data and 32 bits for address lines. The PLB bus standard is designed for high speed and high bandwidth peripherals, and it supports dynamic bus sizing and a programmable burst size. The PLB bus standard peripherals are transportable to microblaze embedded systems supported with other Xilinx FPGAs. This allows designers again to migrate peripherals from one embedded system to another. The PowerPC processor supports both a master and two slave PLB buses. The master bus, that is the bus attached to the MPLB port of the PowerPC, allows the PowerPC 440 processor to access any PLB peripheral placed on it, while the slave bus allows other masters on the slave PLB bus to access the MCI memory, that's a memory controller interface port, and the master PLB V46 bus. The PLB bus supports dynamic bus sizing again as well as programmable burst size. The PowerPC 440 also has a memory controller interface or MCI port, and it's designed to connect directly to the PowerPC processor's DDR2 memory controller. The separate memory interface improves system performance and enables access to a large memory. The PowerPC also has 4 direct memory access or DMA ports. These are commonly used to connect to the tri-mode Ethernet MACs included with the Vertex 5 FPGA families. And again, these are dedicated in silicon in most of our FPGA families. This diagram also shows a pretty typical application in which a designer decided to offload some parts of the embedded system to a microblaze processor. In this case, the PowerPC system had its own PLB master bus and also has a shared slave bus that is also connected to a microblaze core. This is done so that the less time-intensive functions can be offloaded to a separate processor. In this example, that is the microblaze processor. The memory controller attached to the master bus can be customized to support ZBT, DDR, as well as other memory component standards. This, like any other peripheral, can be customized to the memory component with the EDK software. Now, often customers will ask, well, how fast can the system run? That will depend on the number and the size of peripherals, as well as the number of buses that you add to your system. Specifically, again, this boils down to how many LUTs and registers will be required for your entire embedded system, and that will determine how fast each bus will run. In this case, the entire system, except for the PowerPC core, is built with those standard FPGA resources, so the speed will depend on the size of the entire FPGA design and the ability of the implementation tools to place and route the design optimally. In the end, the smaller the system, more likely the faster your various buses will operate. But also in the case of the PowerPC core, usually customers are running their buses at a slower clock rate than they're running the actual processor. Now, as I mentioned, there is a lot of IP included with EDK that applies to both Microblaze as well as the PowerPC 440 processor systems. All of this IP is free, and this includes what you see listed on the slide, including bus infrastructure and bridge cores, memory and memory controller cores, debug components, peripherals, arithmetic functions, timers, components for inter-processor communication, external peripheral controllers, DMA controllers, PCI cores. Well, some of the PCI cores do have a charge associated with them, but as well as though is supported a user core template which allows you to build and customize your own core, your own peripheral. Now let's have a time to actually look at the PowerPC 440 processor in a bit more detail than we've covered so far. This diagram shows the PowerPC processor that is part of the Virtex 5 FXT device family. It is a newer version of the PowerPC 405 that has been part of the Virtex 4 FX family. The 440 is approximately a third faster than the 405. The 440 is a licensed IBM superscalar processor that can execute multiple instructions per clock cycle. The 440 has twice the cache size of the 405, twice the PLB bandwidth. Note the PLB V46 supports 128 bits of data, while the 405's PLB bus supported only 64 bits. The 440 also supports 4 times the APU bandwidth. It also has a dedicated data and instruction cache, a memory management unit, and the 440 CPU. The CPU has a fetch queue and an execution unit. The PowerPC also has dedicated fixed interval timer called the FIT, a programmable interval timer called a PIT, and a watchdog timer. Again, a lot of these features are very similar to the 405. There's also a dedicated JTAG chain as part of the PowerPC. Remember that the PowerPC is just an ASIC fused into the FPGA, so there are actually 2 JTAG chains, one for the PowerPC and one for the FPGA. When I say dedicated, I mean that the JTAG chain is separate from the programmable logic. Well, as we'll see, one of the common questions customers have is how do I connect up the 2 JTAG chains to perform a configuration of the FPGA or to complete software debugging? Well, that's done with the JTAG PPC block component, and it allows you to add this JTAG component when you actually go through the base system builder. Now, like Microblaze, the PowerPC 440 processor works again with the PLB V46 bus standard. The 440 processor core offers the highest performance of any FPGA embedded processor. It also has a hardened processor interconnect structure called the Crossbar switch. This enables simpler implementations and simultaneous non-blocking access. The processor also has a dedicated memory interface that reduces bottlenecks on the PLB bus. The 440 has an enhanced APU that supports double precision floating point functions with key operating systems. This facilitates custom hardware acceleration that eliminates software bottlenecks. In the past, a large arithmetic function would have taken many instructions to implement, maybe perhaps like a large multiply and accumulate or other large math function. But now the integration of custom hardware improves the access to custom hardware that you can now add to your 440 system. While it is really unfair to the customer to pore over the gross detail of the PowerPC 440 processor architecture and recording, I did want to mention some of the features that are significantly improved over the PowerPC 405, as well as answer some frequently asked questions about the PowerPC 440. First of all, it's a 32-bit implementation of the PowerPC processor. The 64-bit operations are not supported in this case. The processor does not implement floating point operations, although a floating point unit can be attached through the arithmetic PU, the APU. Support for embedded system applications has been improved with a flexible memory management component. Multiply and accumulate instructions for computationally intensive applications has already been enhanced. There's a 64-bit time base, there's the FIT timer and the watchdog timer as I mentioned, and of course this processor is a 7-stage highly pipelined processor. and it supports single cycle, multiply, and accumulate arithmetic functions. The PowerPC's APU interface allows hardware accelerating co-processing to improve software and hardware co-design efficiency. This is done by having a separate port on the processor to directly access hardware on the FPGA, which would most likely be to route to the DSP slice or say to a dedicated block RAM. Conceptually, this operates like the fast simplex link that we talked about in the MicroBlaze REL. In this case, what would happen is you would drive out of the processor's port, the APU port that is, you go to some dedicated hardware, do your arithmetic operation, and then feed that data back. And you can do that a lot faster rather than doing it in software, which might take lots and lots of clock cycles to actually complete the arithmetic. Now, integrating this with the DSP slice resources opens the co-processing space for embedded computing in a fraction of the normal hardware development time. And it's also built into the tools to be done relatively easily. Well, as you probably already know, bus masters have the ability to initiate a transaction and effectively can take control of a bus. Slaves only respond to master bus requests. Bus arbitration is a three-step process in which a device requests to become the master by asserting a bus request signal. The arbitration logic, which is programmable for our customers through EDK, monitors the request and provides a grant signal according to the programmable priority scheme. The requesting master samples the grant line and waits for the bus to be released. The master then initiates a data transaction to a slave. The arbitration mechanisms within EDK can be chosen by the designer, and this includes the use of a fixed priority, round robin, or a hybrid system of your choosing. Well, this is an example of a PowerPC 440 embedded system. The 440 processor supports both a master and two slave PLB buses. This system has two primary buses, a master PLB bus and a slave PLB bus. The MPLB, or master PLB, allows the PowerPC 440 processor and any master on the slave PLB to be a master and access devices on the MPLB bus. Now, this is a little confusing because we're used to having a master PLB bus be a bunch of masters, while here it is a pure slave peripheral bus with no master peripherals, as you can see from this diagram. The slave PLB bus does not allow the PowerPC 440 to access any of the peripherals on its bus, and frankly, most typically, customers don't put any slave peripherals on that bus, except in this case they did. It is possible, but not necessarily likely. Now, this is unusual because we're used to having the processor be the master of his entire domain, but in this case, that's simply put not the case. So a really good review question would be, how many masters from the system can access the MPLB bus? Well, in this case, the answer is 3. The PowerPC 440, the Ethernet controller, as well as the MicroBlaze soft processor core that you see attached to the slave PLB bus. Another good review question would be, how many masters can access the slaves on the SPLB bus? The answer is 2, the Ethernet controller and the MicroBlaze core. Recall that the PowerPC 440 does not have access or have the ability to be a master on that bus. Note that the Ethernet controller should be drawn to attach to both the master PLB and the slave PLB because sometimes it's a slave component and needs to communicate on that bus. This would be the same with a PCI core. In fact, if you built a similar system with a base system builder, you'd have the ability to add these components and attach them to the buses the way you'd want. Now, a final couple of notes. The slave PLB bus allows other bus masters to access the memory controller interface, the MCI port, based memory and the devices on the MPLB bus. The DMA master can also access the memory controller interface based memory and the devices on the master PLB bus. All additional masters should be placed on the slave PLB bus, just like we see in the system, so that the MPLB bus will just be purely slave components. You should also note that the MCI port gives 128-bit access to an off-chip memory, and that the 4 DMA ports give 32-bit access to a local link. The DMA is most commonly used to connect to the embedded TEMACs inside of the FPGA that may be dedicated in that FPGA. And those are dedicated, of course, in the Vertex 5 and the Vertex 4 FPGAs. This slide is trying to show the tremendous access the Crossbar switch gives to each of the system peripherals as well as the PowerPC 440. The Crossbar concept simply relieves the problem of busy buses. It is configured as a dual 5-to-1 multiplexer, meaning two independent and simultaneous connections between one of 5 masters to one of 2 slaves can happen at the same time. 3 of the 5 possible masters are the PowerPC 440 processor instruction read, and data write buses. The other 2 possible masters are the outputs of 2 other multiplexers. These identical multiplexers further select between 2 DMA controllers and a PLB bus slave target. Recall that masters can also reside on either of the slave PLB buses. The 2 slave connections to the Crossbar are a memory controller interface, that's the MCI port, to a double data rate RAM controller and the master PLB bus. The PowerPC 440 processor also has 4 direct memory access or DMA ports. These are commonly used to connect to the tri-mode Ethernet MACs included in your FPGA. Each offers a 32-bit channel for each direction and interface to the Crossbar at 128 bits. They can also operate asynchronously with the interconnect clock. They also offer a byte realignment on the TX and RX. They also can be asynchronous with the interconnect clock. They offer an efficient flow control management, and they're also programmable by the processor or the FPGA fabric. The PowerPC 440 processor supports a memory controller interface or MCI port that is designed to connect directly to the DDR2 memory controller of the PowerPC processor. One of the primary advantages of the MCI port is that it guarantees a fixed latency of execution because there is no bus arbitration required. The separate memory interface improves system performance and enables access to larger memories. It supports a FIFO-like interface and performs row bank detection, which simplifies the soft controller logic. It also supports 32, 64, or 128-bit data transfers per cycle. This can be easily connected to a Xilinx memory controller provided with an EDK. Now we're going to have a look at a few examples of this Crossbar switch to get a bit better feel of it. In this example, the separate memory and the I/O buses improve system performance. This is a typical embedded system, a 440 processor, some DDR2 memory, and some peripherals attached to the MPLB bus. Note that the peripherals are connected to the I/O or master PLB. That means any master in the system can access these peripherals. The memory is connected to the memory controller interface bus and is connected to the DDR2 memory controller, and this is connected off-chip to a DDR2 memory. In this case, there is one master device, and that's the PowerPC 440 core, and it can access any of these peripherals. So again, fewer masters, relatively simple system. Well, this system is a little less typical, shall we say. We really wanted to give you a chance to look at some of the EDK memory controllers and talk a little bit about them. First of all, note that the PowerPC slave peripherals are all connected to the MPLB bus. These memory peripherals, as well as the MCI memory, will also be accessible to other masters that are connected to the slave PLB bus. But in this case, there is no slave PLB bus, so it's again pretty simple. Okay, so again, it's not very typical, but you should note that all of these memory controllers are included with EDK, and I just want to mention a few of these. So from left to right in the diagram, the first is the external memory controller or EMC component attached to an off-chip flash device. The next is the multi-port memory controller or MPMC component, and that's attached to an off-chip DDR memory in this case. The next is a block RAM memory controller or block RAM block attached to on-chip block RAMs. The next is another external memory controller or EMC, and that's attached to an off-chip SRAM, unlike the earlier one which was connected to an off-chip flash device. The next component is another multi-port memory controller or MPMC connected to, this time, an off-chip SDRAM, again showing you that this is a programmable device that can interface to different external memories. And lastly, we have a System ACE controller that is retrieving contents from an off-chip System ACE device. Now this is a Xilinx technology. Not as frequently used, but still pretty exciting if you need to store large pieces of memory outside the FPGA. So you might go check it out if you think that might be interesting to you. In this illustration, there are two embedded TEMACs that have been added, and these are attached to the two DMA channels in the upper peripheral block. Now, both TEMACs are potential masters to access the memory controller port or the MPLB bus. Because they're both on the upper master, that is, arbitration logic will be necessary to determine which of the TEMACs will be the master at any given time. Recall that they are connected to the same multiplexer. Sounds like maybe the TEMACs should have been connected to different DMA ports so that the special arbitration would not be necessary. So recall that there is a separate unused multiplexer at the bottom of this diagram. If we'd taken one of those and connected down there, we wouldn't have to worry about that. The TEMACs are connected to the processor block through a thin wrapper that is provided with the embedded development tools and attached to the DMA port. Note that this TEMAC we're building here differs from the XPS_LL TEMAC component, which is attached to the PLB bus. The XPS TEMAC component supports the hard TEMAC included with Vertex 4 and Vertex 5 FPGAs. The XPS TEMAC also supports the soft implementation. That would be one that is not built with dedicated silicon like it might be or would best be in Vertex 5 or Vertex 4, but instead would be built and targeting a different FPGA and would be built with their standard LUTs and registers of FPGA logic. And likewise, that TEMAC, since it's built with LUTs and registers, would be slower than the dedicated one in silicon. Note that the soft version does have a charge associated with it because, again, it's an optimized component. If it's dedicated in silicon, that hard version, as we would call it, would be included for free with the silicon at no extra charge. But as you know, as you buy silicon that has lots more features, there would kind of in effect be a charge with it. Now, adding the TEMACs this way may not currently be supported with the base system builder. The information on that's a little bit old. To be completed, you're probably going to have to manually edit the design. By adding a TEMAC into the base system builder will result in the TEMAC being attached to the PLB bus. In other words, the base system builder defaults to building the TEMAC as being a peripheral on the bus rather than directly being connected to a DMA port. For more information about the hard TEMAC, we want to encourage you to refer to the Vertex 4 Embedded Tri-Mode Ethernet MAC User Guide. And likewise, there's a corresponding document for the Vertex 5 TEMAC. For more information about the soft version of the Ethernet MAC LogicCore IP, check out the LogicCore Tri-Mode Ethernet MAC User Guide. Referencing LogicCore, that means it's a core built from CoreGen and is built with LUTs and registers. So if you're curious about that, have a look at those documents. All Xilinx processor systems have standardized on the PLB V46 bus. In addition, you can have as many microblaze processors in an FPGA as will fit in the device. In this example, the microblaze processor system is attached to a PowerPC processor via a slave PLB bus. This allows the microblaze processor core to access any peripherals attached to the MPLB bus, which is attached to the MPLB port, and memory on the MCI port. But the PowerPC cannot gain access to any of the peripherals attached to the slave PLB bus because this connection cannot be made by the crossbar. This is a simple multi-processing system and illustrates the use of the slave PLB interface, showing that it allows multi-ported access to the memory and I/O of the PowerPC 440 processor block. Now, we want to give you a chance to test your knowledge of the content from the first half of this recorded e-learning. So we're going to take a break from this, take a couple of minutes and complete the quiz we're going to provide you, have a little fun with it, see if you can recall the answers to these questions. Now let's talk a little bit more about the base system builder and its uses with the PowerPC 440 processor. Well, first of all, there are several evaluation and demo boards with Xilinx FPGAs to choose from. Many are made by Xilinx. These usually have the most features, target the largest devices, and are the most expensive. But most are made by Xilinx partners, and there's a short list of these shown here. Well, actually, this is most of them. And those include Avnet, New Horizons, and Digilent. We provide detailed information about each of the available boards on our website. Each board may have different components that you may need as well as support a Vertex or a Spartan device family of your choosing. This will directly affect the cost of the board. Now on this slide we see some of the more popular demo boards, specifically the ones we use in a couple of our classes. The first is the ML507 that supports Vertex 5. We also see the 1600E, which is not necessarily the most popular by any means, but it is one that we support in our courses, which uses a Spartan 3 device. And one of the newest boards is the Spartan 605 or SP605 board. As you may or may not know, the base system builder is designed to make building an initial project quick and easy. It simply allows you to select the demo board of your choosing and quickly build an embedded system through a series of GUIs targeted to that demo board. The BSB is designed to work with all of the currently available demo boards. However, if your tools do not support the board you want, make sure you go to our website and download the necessary board information from our website. This is because not all the board information is available at the time of the software release. As you can see, creating a project is very easy. You can select File, New Project, and then choose to use the BSB utility or to create a starting project. Remember that the BSB utility allows the user to create a design targeted for a specific demo board. The blank project button is used when a customer wants to create a design from scratch and is not planning on using a demo board that is currently available. When you select to create a project and new design using the base system builder, you'll be asked a series of questions about the project, such as what demo board, what processor, how do you want to configure the processor, what I/O interfaces are you going to use, what peripherals do you need, etc. Now this is possible because of course the board has already been made, so if there is an SDRAM on the board, it makes sense to make it easy for a customer to add an SDRAM controller onto the PLB bus, right? Right. Now, after you've answered all the questions, your MHS file will be made for you. You may not recall this, but the MHS is your entire hardware design in a single text file. This is what is changed by EDK when you modify your hardware design. All of your peripherals and their chosen options are also stored in this single text file. I mention this because the MHS is user editable, although it is not necessarily recommended for that use. But I still encourage you to crack the file open and have a look. The syntax is pretty simple. Now the BSB will also create a test app file which contains a simple C source code to test your hardware and is ready for download. The base system builder will also generate a UCF file which contains your final pin assignments and pin attributes as well as timing constraints for your demo board. Now it is a standard file used in all FPGA designs. Like the MHS, I encourage designers to open this file as well and review its contents. Like the MHS, it is user editable, but is easier to change when you use the Xilinx Constraints Editor. But that is accessible from the ISE tools, not from within EDK. The UCF file also contains your design's timing constraints. These are used to communicate to the implementation tools how fast you want the parts of your design to operate, and most specifically it's going to make a global constraint for each of the clock domains. So if your processor system has two different clock domains, one for buses and peripherals and one for the processor, then the tools are going to have a timing constraint associated with each when you use the BSB. So this is a good thing. It's going to save a lot of effort and a lot of understanding. Now, as you can see from the lower screenshot, you can also specify a peripheral repository directory. Now, this is useful if you have built a library of custom peripherals that you may want to add to the design later. Well, if you haven't, most likely you're going to want to do that. Most customers do want to build a custom peripheral to add to their embedded system down the road. Now, we cover building and optimizing a custom peripheral as part of our standard embedded system design course. But once you've made that IP, a lot of customers like to make that IP available to all their designers, and so they'll use this repository to keep all that IP. Now, after you've chosen your board, the next step in the base system builder is to select the demo board with the GUI. This GUI will then also quickly allow you to learn more about all the available demo boards, since all the technical information about each demo board is already installed. So as an FYI, one of the things you can use is use the base system builder just to shop and find out the different demo boards that are currently available and go through and learn about all their features. Now, the BSB also makes it easy to install the necessary BSB information for the most recent and thus not installed demo boards. You can even customize the BSB to create your own custom demo board if you would like. Now, we're not going to have enough time to go through all the GUIs that are supported with the BSB, but suffice to say there's about 8 or 9 pages of options to modify for your demo board. Now, I want you to note at the top of the screenshot there's a little green dash bar at the top. That tells you where you are in this process with the BSB. It allows you to build both a microblaze as well as a PowerPC 440 embedded system. You can also build a dual processor system. This could include multiple microblaze or PowerPC cores, or even one of each. Now, as you can see, the GUI then shows you a representation of your system so you can better understand the resources that would be involved. The BSB will even ask how you want your peripherals connected to the buses and which peripherals should be shared. Pretty smart, eh? That is important because the PowerPC 440 has different ports for connecting a master or a slave bus, and how you set up your system will determine whether or not one peripheral or master device can communicate with another. So the implication is that the BSB is going to make it easier for you to build an embedded system that you can actually use. Now, also keep in mind that the ability to use the PowerPC 440 processor, again, is still dependent that you're going to be purchasing a Vertex 5 FX device. Depending on your processor, you'll then be asked to configure the processor. One of the most important options is the clock frequency that you plan to connect the processor to. The GUI will allow you to specify a different processor and bus frequency if you're targeting the PowerPC 440. But don't forget that the requirements for your bus frequency are dependent on the PLB v46 bus standard. So generally, most integer relationships between the frequencies are supported, generally 1 to 4, where the highest frequency would be connected to the processor itself, say the processor at 400, and the lower frequency to the buses, say 100. The BSB in this case will also write a global timing constraint for each clock signal in the UCF. That will guide the implementation tools to manipulate the place and route solution so the system timing can be met. But the real question again is, how fast will the system run? The answer is that it simply depends on the number of peripherals and how many buses your design has. Simply put, more logic, the lower the maximum speed. It also depends on the family the FPGA you're targeting and, of course, the speed grade. Recall that each family has different performance. However, to get peak performance, most designers are only adding a couple of peripherals to the system. If your system is like that, then top speed should not be that difficult, but unfortunately you won't know until you build the hardware and try to place and route the design. Fortunately, using the base system builder to build your system is very fast, so typical system hardware can be built in under 30 minutes. Now all you need to do is add the rest of your FPGA design to the logic and then go through place and route. And of course, depending upon whether or not you have that remaining logic will determine how fast that will actually run through implementation, how fast the system will be. Now lastly, note the debug interface option at the bottom of the GUI. This allows you to insert access to your embedded system through the FPGA JTAG chain, which is recommended for the PowerPC 440. Now this is done with the addition of a simple component in the MHS file called the JTAG_PPC block. By asserting this button, it will be included and hooked to the FPGA internal boundary scan components for visibility on the FPGA's JTAG pins, which is necessary for software debugging. So basically what it does is it connects together the FPGA's JTAG chain as well as the PowerPC's JTAG chain. This GUI allows you to add peripherals to interface to the various components your demo board has. So for example, if you have a series of push buttons or LEDs, you'll have the option to add a general purpose I/O peripheral to your system. In this case, only the peripherals that are available for this demo board are available in the left-hand column. To add a peripheral or external memory controller, simply drag it from the left-hand column to the right-hand column. To modify the core's parameters, you can simply double-click it after adding it to your system. Note that not all of the I/O interfaces are required for your use. Likewise, internal peripherals, that is, those peripherals that don't connect to I/O pins, can be added to any design on any demo board, of course as long as you have enough FPGA resources to add the component. Now, most peripherals support the use of interrupts, and EDK supports you adding a custom interrupt controller, and that is one of the labs as well as one of the discussions we have as part of our standard embedded system design course. How to add an interrupt controller. Once you've configured your demo board's embedded design, the BSB will generate an MHS or microprocessor hardware system file. This will contain all the components of your embedded design in one simple text file, including buses, peripherals, processors, and each component's attributes. This file is used as an input to the PlatGen utility to create your embedded system's netlists. PlatGen will create a netlist and an HDL instantiation for each component in your embedded system. This will be used by the implementation tools, that's the ISE tools, when completing your FPGA's place and route. PlatGen also generates your embedded system's top-level system HDL instantiation. This allows the embedded system to be automatically integrated with the rest of your embedded design, just like any other component in a top-level HDL design. And all of this is done when you run the command hardware generate netlist from the horizontal toolbar. Crossbar switch speed system performance utilizing an alternative architecture to the bus that is 120 bits wide. The crossbar clock is usually the fastest in your embedded system. All other embedded clocks are relative to the crossbar clock, that is the bus, the memory, and the DMA. The PowerPC 440 processor supports the attachment of one master PLB bus for connection to slave peripherals and two slave PLB buses for connection to other system master components. The 440 processor has a memory controller interface or MCI port, and this allows the fastest memory access possible by connecting to a Xilinx memory controller. The 440 processor has 4 DMA or direct memory access controller ports. It also has an APU which supports coprocessors being built in FPGA fabric. Well, there are lots of places to learn more about embedded processing, and they all start at support.xilinx.com/embedded. This includes learning more about the currently available embedded design kits or demo boards. Now, don't forget to check out the documents I'm about to cover. When you get the tools installed and go to the web page, you're going to find them pretty useful. The first thing is the Getting Started has good installation, basic tool instructions. This will also re-explain the base system builder utility in more detail, just in case you're still a little confused from what we just covered. The Processor IP Reference Guide discusses all the peripherals included with EDK, discusses device utilization, features, parameters, how I can customize it, etc. What are the default parameter settings? You can also just right-click on each peripheral from within EDK to learn more about each piece of peripherals functionality. Now, the Embedded System Tools Guide covers everything about EDK. The drivers document goes hand in hand with the IP guide to explain all the software functionality we include with each peripheral. That's right, with each peripheral you also get a library of drivers. The drivers are used by your software engineers to build their software code to access that IP. Now, this is the most commonly used document by software developers, so do yourself a favor, point them to that document once you've got the tools installed in their machine. Note that we didn't go into really any detail into the EDK software except for the base system builder utility. We simply did not have enough time. But if you have questions about their architecture of the processors, check out the reference guides. Don't forget that there is also an EDK online documentation page that is accessible directly from EDK. To get there, again, just click on the Help icon and the horizontal toolbar in the upper right-hand corner, and go Help EDK Online Documentation, and that'll pretty much take you to all this documentation on our web page. Or you can go outside through your browser. In general, all the EDK documentation and application notes are on the EDK homepage. So we encourage you to check both those sites out. I think you'll go back there pretty frequently at first. Where can you learn more? Well, if you would like to see what other courses we offer, or what other free RELs are available, go to the Xilinx education link that you see here. I wanted to mention to you a couple of our courses that we offer. We offer 3 of them currently that are focused around embedded design. The first one is the Embedded Systems Development course. It's our most fundamental. It covers both hardware and software flows and really introduces the basic functionality of the tools, both hardware and software. I find that most software engineers end up getting bored the first day because it's all hardware and they don't care about it. And I've noticed that there's plenty of hardware designers who care about the first day, don't care so much about software, and that can sometimes be a little bit of a problem. But frankly, I find most software engineers would rather go to the Embedded Systems Software Development course, which is the second one listed here, which has got a pure software focus around our SDK software development kit. So that's probably a recommend a software engineer to go to. But the first course really works very well for hardware engineers because we do still cover software, and I do find that most of our customers are having one engineer do both the hardware and the software. But there's a number of corporations that they divide that work up. So choose the appropriate course for you. But I've yet to have a customer tell me taking the first Embedded Systems Development course was a waste of time. That just has not happened to me. The last course we'll see at the bottom is the Advanced Embedded Systems Development course. This is, again, really more about hardware than software, and it covers a lot of the tools, flows, and functionality that we didn't have enough time to cover in our first Embedded Systems Development course. So rather than calling it advanced, I might call it a reservoir of information that you do care about, but we couldn't fit into the first course because it wasn't as important as the content we cover in the Embedded Systems Development course. But I would probably tell you that if you wanted to take both courses back to back, both Embedded Systems and the Advanced Embedded Systems, that's not going to be a problem, because if you're trying to use chip scope or do an off-chip flash, which a lot of people are doing, you have to take that second class anyway. So keep that in mind. It's not necessarily advanced, and I wouldn't be reluctant in signing you up right away if you wanted to do both, but you must go through the first Embedded Systems Development course. I think you'll find that the most useful. Well, where can you learn more? Well, we give you a number of links here. First one here is very important. Do us a favor, and before you go, please take a second and let us know what you thought of this REL. Did you find the content useful? Was it too fast, too much, too little? Just click on the icon and let us know what you think. And likewise, when you're giving us feedback, if you've got a suggestion for another REL topic you'd love to see, please let us know that. You'll also know that you can get various locations here. You can go to the course details page, or you can just go back to the training page on our website to learn more about our courses and RELs as well. The related RELs I mentioned are also located at the bottom. You can get to those, or likewise go to our training page and find your way there. Again, I want to thank you. I'm sorry this REL was so long, but the simple fact of the matter is I didn't want to shortchange people, and there's a lot of content to cover here. So I think you've really gotten a good introduction to the PowerPC and some of the things you have to consider. I appreciate your time. Again, my name is Frank Nelson. You've been listening to the Embedded Design with a PowerPC 440 processor core recorded e-learning. Again, thank you for listening, and thanks for your attention, and most importantly, thanks for your business.